the hurdles that welcome. I was going to waffle about how Zoom makes it difficult to hit the record button, but you did it.
It's not like one of those things that moves the button around as you move your mouse over it, so that's fine. Redirecting to YouTube. Oh, wow, I think we're live on the internet. Incredible. Hi, Molly. Cool, I can see myself. Amazing. We are totally live on the internet. Okay, welcome everyone to the, oh God, I'm just gonna mute it. Okay, cool. Okay, welcome everyone to the IPFS weekly call for Monday, the 2nd of September, 2019. This is going to be fun. I am Aching Brain. I am your host for all of September, having taken over from the venerable, he's not that old, Ollie Evans, who's done generally a great job. Cool. So we have we have some announcements. We have one announcement, and then we have a super interesting talk from top of hours of Quorum Control. Very much looking forward to that. So the one announcement is a call for help, a cry for help to create a next generation navigation system for docs.ipfs.io. That would be super good. If you are interested in that, get involved. We need your help. There's going to be a video call. The URL is in the docs, so I'm not going to read it out. It's on the 6th of September from 5 p.m. till 6:30 UTC. Cool. Wow, it flies. Okay, cool. Great. With that, I'm going to pass over to Topper, and you can tell us all about Tupelo. Over to you.
Thanks, and hi everyone. It looks like we're a small group here, so one, feel free to interrupt me, and two, I have a little bit of a cold, so if I said something you don't understand, just also interrupt me and say, what did you say? And I'll repeat it. I think what I'm going to do is give a little background. I have a couple of short slides of just what Tupelo is, and then I'm going to try and concentrate most of it on actually, against all the demo gods, doing a live demo here against our testnet. Because I think that'll help illustrate some of the more protocol lab specific stuff, the IPLD and libp2p and all that kind of stuff. I think more than slides will. Just seeing things change is always makes that kind of thing click for me. So with that, I will start there. And I need to share my screen or else you won't be able to see it. All right. And you're hovering over my present button. All right, everyone can see introducing Tupelo here? Yeah, okay. So I'm Topper Bowers. I'm the CEO of Quorum Control, which is a for-profit company building an open and permissionless Tupelo network, which is a new layer 1 DLT platform that is purpose-built for real-world objects and applications as opposed to finance and decentralized finance. And I think to illustrate that, it helps to talk a little bit about existing tech here. And I'm going to go kind of quickly through this stuff. So feel free if there's, if there's questions, then I will back up and answer those. But I think it's interesting to talk about Tupelo in comparison to existing tech. And the way almost every current blockchain works is that there's a chain of blocks, right? And inside of that block, every transaction is put into an order, right? So there's transaction A, transaction B, transaction C, and those are put into order by, in Bitcoin, that would be miners, and some other thing that would be validators. And they do a lot of work to try and be fair about putting those transactions into order. And they have to do a lot of work in total ordering, which I'm sure there's a lot of developers here. Total ordering is a really hard problem in decentralized systems. And so they spend a lot of effort to make that happen. And the reason why they have to do that usually is because of what's called the double spend problem in traditional DLT, which means that if Alice is paying Bob and Alice is also trying to pay Carol, you need to see which one of those transactions came first to see whether Bob whether Alice paid Bob or whether Alice paid Carol, right? And so they spent a lot of work just to make sure that those transactions happen in the correct order, so that Alice can't ever spend more than more than her balance of tokens, and that only one of Bob or Carol get paid. And that's kind of the reason why they started out doing this whole global total ordering. But then what we started to do with DLT is to put all sorts of other crazy stuff on it. This is a picture of a weather station, right? And so what we, some people have started to put weather data into blockchains, and the thing is that the underlying system goes through all the same process, even with this weather data, right? So not only is it doing the order of the weather data, but it's also putting Alice and Bob's transactions in order with the weather data, right? So this is like totally unnecessary work for the system to do. No one cares whether the weather data came before Alice's payment or after Alice's payment. And additionally, blockchains are awesome at keeping data in perpetuity, but they also have to keep data in perpetuity. So all this weather data or whatever kind of data that's in the blockchain is kept around forever, which I think at the time of creation, maybe made sense for an auditable blockchain specifically for money. But when you start talking about applications, it becomes a different kind of concern. It's like whether this data should exist forever. In some cases it should, but it's not always, right? The weather data every 5 seconds doesn't need to be kept globally on 25,000 computers forever and ever. And I kind of ran into these problems myself when I was trying to build an InfoSec company, which was the sort of Quorum Control original flavor, as I say to my team, which was a security company, and I was trying to anchor trust from any public blockchain to a corporate set of security rules. And what I just realized was that for the business, it was just really not going to work. And I was looking at everything. This is back in 2016, so the choices were more limited, but there was still a lot. There was still Bitcoin and Ethereum and what's now called Nano, which at the time was called Ray blocks, and there's all these other esoteric high-speed ones. And what I realized is that almost all of them weren't going to work. Well, none of them were going to work for the business for a variety of reasons. One, all the transactions were costly, and costly in like the worst possible way too, right? Like variable cost. Sometimes they cost a penny, and sometimes they cost $40 or $100. And so when you're trying to bake that into the cost of running an application, that becomes really hard. Also inflexible. In some cases, like Bitcoin, it's very inflexible. But in other cases too, you're always writing smart contracts, and the problem with smart contracts they're great in some certain cases and are in fact necessary in some certain cases, but in the 90% case, people are rewriting the same thing over and over again, which is like, here's this object, here's some data about that object, here's who owns the object, and that's about it. And so when you're talking about any kind of real world application, like that weather data, like a supply chain, like any kind of track and trace system, even stuff like CryptoKitties, all of that stuff is really just a CRUD application that people are writing complex, insecure smart contracts for. And then the unscalable is the one we all know and love, right? It's like 7 transactions a second, and the electricity consumption of, I don't even know what it's up to, Ireland or something like that nowadays. And so Tupelo is pretty different. It models each individual object in this data structure, which I'll get into more detail in a second, called a chain tree. And those objects are completely separate from all the other objects in the system. A chain tree is a combination of a blockchain and a tree of current state, all summed up into a single IPLD object, so Merkleized into a single tip. And what that gives you is that you have the tree of current state and plus the history of all changes to that data structure, contained in a single data structure, and it doesn't have to interact with any other chain trees to have its own state be verifiable. And because we can define, Tupelo defines some certain transactions you can take on those chain trees, which I'll get to in a second again, but basically, it provides the ability to set data, set who owns this chain tree, and then do some token work on that chain tree, which again, I'll get into in a second. But the big deal with having individual objects modeled separately is that the consensus algorithm can be much simpler and much faster. Also, transactions can happen asynchronously. So when a transaction happens on one chain tree, we don't have to wait for a block. We don't have to wait for transactions in 3 other chain trees to happen. We can deal with that single transaction, which again speeds up the whole process and doesn't have unnecessary work. So yeah, we have a new chain tree, new data structure called a chain tree. We have our own consensus algorithm, which is, I mean, it's not entirely our own. It's based on other people's good work. I wouldn't want to sit here and say that we developed completely our own consensus algorithm, but what we were able to do is simplify BFT proposals down to lowering message complexity, and also having this like asynchronous ability here. And because of IPLD, we have this other cool thing, which is that the signers, which is like our version of validators, don't actually need to keep the history of the blockchain around. What they do is they keep basically a hash table of a ID of the chain tree and its current tip. And so what that means though is that when the next transaction comes in, the chain tree can pass back in any relevant state that is needed for that transaction. So that can be a little complicated. So stop me if that doesn't make sense to anybody, but the signers have only a tip. And if you want to do something that requires state, you can pass back in that state. And because the signers have the tip, they can verify that the data you're passing back in is their previous view of the world. So you have this cool thing where signers do very little work and store very little data to do a global consensus. And then Tupelo is not a smart contract platform, but you can end up doing some extremely complicated applications on top of Tupelo because of these simple transactions of set data. Here, actually, just go there quickly. You guys, set data, set ownership, establish token, mint token, send token, receive token. Allows you to do all sorts of real world use cases, all sorts of like digital use cases with that set data and set ownership. And then all sorts of the kind of like token economy thing that you expect from a DLT with the token transactions. So, as I said, Tupelo can consider each transaction that is coming in isolation. What that ends up being is that the whole thing is faster. Because also that their signers are not having to keep a ton of old state around, the transactions can be cheaper. It's also proof of stake, not proof of work. So the signers actually don't do a ton of work on each transaction, and so they can be modeled as like super cheap transactions for signers to break even on. And because there's no smart contracts, and it feels a lot more like using an API. With this crowd, I'll dive into a little more detail on that. What you're actually doing is sending a message to the peer-to-peer like pub sub network. But from a programming language, it feels like you're like calling an API and getting that tip back, like the signed tip of your chain tree, which I'll show you in actual code in a second. This is what a kind of a conceptual view of a chain tree. There's the root, which points to a chain and a tree. This one on the left would probably be better off horizontal, but it's like, it's a normal blockchain. There's the last block and it goes out to the first block. The tree points to a user settable data section, which the user can do whatever it wants. And this underscore Tupelo section where changes are, well, the whole thing is a finite state machine. This has in particular has limited rules. Users can't arbitrarily change this underscore Tupelo because it has to do with the tokens and the ownership. So they have to take specific transactions on this underscore Tupelo section. So chain trees are finite state machines, and they transition from one state to another. So from in IPLD speak, from one tip to another by using a transaction. Well, actually by appending a block to the chain section, which is a list of transactions. You play those transactions against the chain tree, you get a new tip, and then the signers in the network sign that tip. And then the world can know what the new state of your chain tree is. So I already went through these. And I can demo now, but I'll pause there. Is there any questions that people have right now? Okay. So we have a new SDK, which is our Tupelo Wasm SDK, which is, it's kind of cool. It's actually, this SDK uses, I think, like all of Go and all of JavaScript of Protocol Labs, libp2p and IPLD. So rather than having to redo how the transactions happen in JavaScript, we have a Wasm file generated from Go. Go also does stuff like walk the hash array maps tree, but then uses JavaScript to do stuff like do the block service and the block service and the pub sub and the actual libp2p node is all stays in JavaScript land. So using that, we have also this Explorer and wallet, and I'll show you in a second. Can everyone read this on my screen here? Cool, yes, okay. We can see it's pretty easy. So this we get a community, which is a layer on top of Tupelo, the actual like consensus algorithms of Tupelo that provides some things for the pub sub network and also for some storage for the public members. We run a community member now. This community layer is decentralized like email as opposed to DLT. Like anyone can run one of these nodes. Where Tupelo itself is a proof of stake system where people have to stake coin to become signers. A key is what owns a chain tree, and a chain tree that Tupelo doesn't know about is owned by the first key that creates it. That's what creates this a DID of it, decentralized identifier. And so in this example, what we're going to do is we're going to create a key, and we're going to create a trading card, so a chain tree that represents a trading card. We're passing in a block service, which is just a regular IPFS block service in this key. You'll see we're setting the property of the trading card ID, and then we're going to make a block. So this play transactions creates a block on the trading card tree, and we're going to do 3 set data transactions. So we're setting /series to that, /item to number 48 here, and /condition to mint condition. There are 3 community members. We're just waiting for those to update. Then we get the ID again, and then we go back to Tupelo and get the new tip as known by the signing members. And we'll see that new tip here. Those are assertions which won't show up, and we'll see here successfully registered. So assuming that everything goes well, and you'll see, and this is actually running against our real testnet here too, not against the local of mine. So you can see the speed of that kind of thing. And this is finality too. It's not probabilistic. This happened, can't be undone. And you'll see the new tip, card was successfully registered. So we take the DID, and if we go back to this, also I should point out, so this app that we're going to use here, actually, so let me see, is that 0C4? Yep. Okay, so that's this one. Double check. Yep. Okay. This app has no server. I mean, it's running on GitHub IO, so I guess that is a server. But I mean, there's no like backend server. It's all front end and Wasm running in the browser here. And so this is the chain tree explorer. So you can see here's the DID of the chain tree we made, and the tree. If we can click into it, tree data. And then here's the item, series, and condition that we set here. You also see the chain side is not quite as pretty, but if we click to the chain, we can go to the end. And this is we did that's the signature from Alice, and then a list of transactions, which there were 3 of them, and you can see like the set data payload, which is a path, and the value, which is a buffer here. And those are passed in order to set the chain of the chain tree. Another just quick one here, we'll do ownership transfer. So with this one, we get the community, we get Alice's key. Alice gets a trading card of her own. Bob gets a key. Bob gets an address, and then Alice immediately, the first transaction is to change the owner of the trading card over to Bob. And so we'll do that. But you know what? That doesn't tell us which card it is, so that's not very helpful. Let's do that. And then we'll just add a trading card.id. Okay, we'll go back here and do that again. This is a new trading card. I'm not changing a different one. So, okay, so we go here and we get in here. Okay, then we go to the tree with this one. And now I see this one has the underscore Tupelo that I was talking about before. And authentications. And this is Bob's address. And so only Bob, whose key matches this address, may make any changes to this chain tree in the world. And tokens. So quickly look at the code here. Tokens, we're going to create a chain tree, Alice's and Bob's. And we will do, make sure we get the ID this time around. Okay, and then we're gonna, each chain tree can mint its own tokens, and it has sort of human readable names or arbitrary names inside of the chain tree, unique to that chain, like it has to be unique within the chain tree. But then the full token name is the full chain tree DID : token, which means, so that allows you to do kind of interesting things. Like if you have a piece of artwork represented by a chain tree, you could have those tokens be shares. Other things you can do with them is like usage tokens. Like we actually have a scooter company building, and they're going to use these tokens to represent, like, you're allowed to ride on a scooter, that kind of thing. Excuse me. So then you establish a token, and the reason why you establish is so that you can have a maximum amount ever created. That's the only monetary policy we currently support, but we're looking at it with others. And then you mint, so this is going to mint one token, and then it sends it over to Bob, and then Bob does a receive token. And that actually is one difference, because we don't have this total ordering. We do need to establish a relationship between send and receive. And so we have a send transaction that happens, and you get a receipt of that, and then you give it to the next person, and they do a receive transaction. And so it's like send, off-chain, send the payload, and then a receive transaction. And what that does is establishes an order between two transactions that do actually need to have an order, but only between those two. So let's go see tokens. And we can go here and tree, Tupelo, tokens, and you can see that there's this Alice token here now. And I know we're coming up quickly on time here, so I'll just do a quick, this is like a wallet representation of that same thing, basically, different chain tree than we're working with. But you can see, you can establish token, IPFS token, and we'll make it so that there's only, how many people are on here? 10 ever to be allowed. I have to refresh right now. UI is not perfect in all of this. But now there's this IPFS token with a max of 10. We can mint 5 of them. And now there's a balance of 5, and we can send them to someone with a DID. And all of that is happening in the same systems that you saw. So I think that's my quick overview there. We use libp2p underneath with pub/sub. It's a separate network up from IPFS only because of the IPFS DHT. It's too hard to have nodes find each other on there right now. If that was ever fixed, we could probably just have to operate directly on the IPFS network. And the whole, I mean, chain trees are built entirely on IPLD, right? I mean, it would be reinventing the wheel to do them with some other different technology. And then we use, bit swap. We don't actually have a full IPFS node, but we use libp2p with a bit swap attached around there to do this kind of like changing, like for the explorers and things like that here. And I think that's my overview since we're coming up on time here. So any questions?
Oh, what?
Hey, thanks for this. I'm trying to wrap my head around the way that you get around the total ordering and also like the implications of that. Is the main like innovation decoupling the send and receive?
So decoupling the send and receive allows for the tokens to establish an order again. But for like things like set data and stuff, there's no you don't have to have any total ordering, right? Like the transaction just happen. But yeah, the decoupling the send and receive is for sure what allows on the receive end to know, like it's like a cashier's check. Actually, I don't know how many US people are on here, and Europeans tend to not know what that is. But so it's like if the send token actually deducts the balance from the chain tree at that time. And then you have this payload, which doesn't need to be kept secure because it's like written to the receiver. And then when the receiver goes to receive, the network has already signed the send. And so you're establishing this order between the two of them again. Does that make sense?
Yeah, I think so. And the main benefit, yeah, what is the main benefit for removing the total order? Does that have to do with like the work that the validators do? Exactly.
Yeah, the validators don't have to do, coming to an agreement on order is much harder than coming to an agreement on partial order. And you can see that in all of the, all of us are rebuilding stuff that was studied in the 90s. And if you look at that documentation back then, like a lot of people came up with partial order systems pretty quickly, but coming into the total ordering was much harder. And this allows us to skip that whole section, which actually means that we can skip around in practical Byzantine fault tolerance, we can skip the confirm stage.
Okay, so this reaches into the consensus layer.
Yeah, the consensus layer has to do less work, and therefore it can lose around in the consensus. Yeah.
All right, thank you.
Yep.
Cool. I think we are out of time. I'd like to say thank you very much to Topper for coming on and talking about Tupelo. That was super interesting. So a round of applause from everyone, please. Yeah, fantastic. Thanks. So next week we've got Dirk, and he's going to talk about improvement he's making to BitSwap, which is going to be super interesting. Cool. Thank you very much. I've Naking Brain. This has been the IPFS Weekly Call for the 2nd of September 2019. Bye.